Hi, everybody. This lecture, we're going to discuss the properties of continuous time Fourier transform. There are many properties that help us to find the Fourier transform of signals without going through the integration or going through the transform pairs. So properties can be used efficiently to find Fourier transform some function that they are related. Let me just give you examples using this table. This table, by the way, it's in the handout that I published on the Fourier system. It has most of the properties you're going to use. For example, here, when we look for the first one, linearity, if you are adding two signals time domain, it will be the sum of their Fourier transforms too. And there's time shift when xt minus t naught here, then and you know x omega, it means you know it's Fourier transform, you just multiply it by e bar minus g omega t naught. Of course, it's not, I mean, really, I mean, if we go through it and read for you, you will not just understand it. So let's just take one example and see how can we use the properties to find Fourier transform for some function related to the given one. So let's say that the function, the original function given x of t was e power minus 2t ut. And we know from the table or use Fourier integral, we found its Fourier transform x capital omega is equal to 1 over 2 plus g omega. So now x of omega is given. But now, maybe the question will to find some function, to find the Fourier of some function is related to the original one given to us. Like, now say find y omega, it means find the Fourier transform of another function, of the signal y of t, when, let's say that yt was given like e to the power of minus 2 t minus 3 ut minus 3. So it's a new function, but when you look at it, it's related to the original one. That's e minus t to the original one and multiplied by ut. But this one is the same, but just, I mean, the time, there is a time shift here, 3 from each time. T is subtract minus 3. We have property, if you look at the table, and you will have the table with you when you're solving the problem. You'll find that if you want to find the Fourier transform of a signal that's shifted by t naught, the corresponding is you just find the original one and multiply it by e minus j omega t naught. Well, in this case, that's our x omega, the original function. And this is the function where t is replaced by t minus 3. So t naught here is equal to 3. So t in our example, t naught is equal to 3. Accordingly, we can find now for the new value, for a new function y of t will be equal e minus j omega t naught is equal to 3. So it'll be 3 omega. So let's write it the right way. It will be equal to 3 omega. And x omega is given 1 over 2 plus j omega. So that's it. You see how easy the property? You don't have to go through the integration or you go to the table of the transform pairs. Just use the property so you can find a new function. But the condition is the new function should be related to the function which is Fourier transform is given, right? Let's take we'll take about a couple of them because I mean there are many, but I can't do in one video in all of them. But I'm showing you how can you implement. Let's say that we want to find y omega where y of t is defined as e to the power of 2t u minus t. Then when you look at the new function here, And the old one was given x of t, I'll just write here, is equal e minus 2t ut. So what you observe, what is the relation between the new function and the old function? T is replaced by minus t. So when you replace minus t, it becomes 2 positive 2t, u of t become u minus t. So you look for the table for the property. Yes, there is a property that if you want to find the transform of x minus t, you write x of omega and just replace every omega by minus omega. Makes sense. So what we are going to do here? Well, remember that transform of this function is equal 1 over 2 plus j omega. That's your x omega. So according to this new one, so y of omega, we'll just write the same thing. The only thing we're going to do, we're going to replace omega by minus omega. So the answer will be 2 minus j omega. And observe here, when you are changing from t to minus t, only the negative sign change with the j omega. What does it mean? It means the magnitude will not change of the frequency component, because when you take the magnitude, you get the modulus, you get square root, square both. So it will not affect the magnitude, but the phase will be affected. That's when you do. Just, I mean, that's one observation. Well, let's find another one. I'll give you something, maybe it will feel tricky, like, I mean, find the Fourier transform of 1 over 2 plus jt. Now this is strange because it's given, like, I mean, not like e to t or minus to t. You will never expect that this is really related. No, it's related. How is it related? This, I mean, function here of time, it's very similar to the one given in omega, but just omega replaced with t. This is 1 over 2 plus j omega, and this 1 over 2 plus jt. So it's the same, but just omega it's changed with t. So do we have something? Yes. There is a property that, I mean, if you have the capital X, means that the Fourier transform, and you replace omega by t, and then you want to find the Fourier transform of this one, because it's a function of time now. So you will get x small, it means you get the function of time and replace time by minus omega and then multiply it by 2 pi. You didn't get it? Let's do it in this example. In this example, we want to find the Fourier transform of 1 over 2 plus gt, and it means that you want to find the transform of the x capital, but instead of omega, you put t. So I will apply this. I will say 2 pi times will be equal to 2 pi times x small. What's x small? Okay, x small is the time domain, which is equal to e minus 2t. Let me write first and then time, e minus 2t ut. But here it said replace t by minus omega. All right, so just I'll go. If I replace this is by minus omega, the first one is easy. All right, replace here t by minus omega, minus be positive, so to be positive 2 omega. That's it. So that will be the answer. So this is strange, but I mean, it's very simple when you know. Well, let's take one more. What about if they ask about find the Fourier transform of the differentiation of the function itself? Of course, if you want to do it in the normal way, it would take a long time. You differentiate e power to t, and then you do the integration. It takes a long time. But there is a property for that. They did that already. They prove it. They say that if you want to find the Fourier transform for the differentiation of any function, the corresponding Fourier series will be like the same x omega, the same Fourier transform you got it for the original function, and just multiply it by j omega. That's interesting. So if you want to find Fourier transform for the differentiation of e to the power of, what's the original function? The original, minus 2t, e minus 2t ut So the answer will be, I'll find x omega. I know x omega will find 1 over 2 plus j omega multiplied by j omega. That's it. So I mean, just make it look nice. J omega divided by 2 plus j omega. That would be the answer. Simple. You don't have to do any integration. So using, understanding the properties, how to use it, it really saves lots of time. Well, if you want to find the second differentiation, what you'll do? All right. So you multiply it again, whatever you got here, multiply by another j omega. Every time you differentiate, multiply by j omega. That's all. All right. I'm just focusing on some important properties, but there are many. You will see, I mean, right, 2 or 3 pages full. You have the sheet and just apply it, and then the homework, do the homework. That's the practice exercise. Really, I mean, good. Now, what about integration? If you want to integrate, find the Fourier transform of the integration of the same function that we have from minus infinity to t, e power minus 2t ut dt. So what's the integration of this one? Do we have something? Yes, we have. There is a rule. It said that if you want to integrate a function and then you want to find its Fourier transform, you will do the following. First, remember in differentiation, you multiply by j omega. In integration, you divide by j omega. Easy. J omega x omega. But if you know that integration, I mean, we have the initial condition. So that's what we're going to do, plus the initial condition, which is equal pi x capital of 0 multiplied by delta omega. Well, that's a long one. Yeah, this is one, I mean, because of the initial condition. Let's see how we'll do that. Well, our function is, let me write it down. The transform for our function is equal to 2 plus j omega for this one. So when you do the integration, I will say equal to 1 over j omega multiplied by x omega, which is 1 over 2 plus j omega, plus pi x of 0, x capital. That's x of omega, that's x capital. So if you just have to omega equals 0. So x capital of 0 is 1 over 2, because omega will be 0 here. So pi over 2 delta omega. And that's it. So that's the integration, all right? So, I mean, that's, I mean, just I show you, I mean, the properties. There's another really very interesting and important property about the convolution, and I will do it in a separate video, not to make this one long, right? And you have a project from MATLAB that you are going to use different application with modulation that's using communication, all right? So make sure that you can do that. See you in the next video.